So I start. Welcome everyone. This is the third webinar organized by the WCRP Explaining and Predicting Air System Change Lighthouse Activity. I'm Annalisa Kerchi from the Institute of the Atmospheric Sciences and Climate at the National Research Council of Italy. And I'll be one of the moderators of this event today. Before getting started with the presentation, we want just to remind you the goals of the webinar, of this webinar series, and the goals are to provide a discussion forum on topics related to the EPESC activity objectives and to support the implementation and development of the scientific agenda that will be taken forward by the Lighthouse activity and the partners co-organizing this series. This is the third of a series of webinars. We have the first one last September on record-breaking extreme events, and another one, the second, last November, on the triple La Niña. While today we are focusing on explaining and predicting global and regional changes in droughts. And we will have a presentation that will cover global analysis of drought, and then two sort of examples or specific analysis dedicated to regions for where drought are very important. So Africa, and especially the Sahel region and South America. Before starting, I just want to do some advertising because these topics will be, among other, fully explored at the WCRP Open Science Conference that will take place in Kigali in October. And so this is the advertisement. And just to remind you that the abstract submission is still open and the deadline is on the 28th of February. And if you want more details, and you can register to receive further notification about the conference, and you can visit the website. I think that the link can be posted on the chat, so you can have a look at there. So I have done for now, so I'm going to pass the word to our other moderator today, that is Matilde Rusticucci.
Thanks. Hello and warm welcome also from my side. I am Matilde Rusticucci from University of Buenos Aires in Argentina. Before I introduce our first speaker, I'll provide an overview of today's events and modes for interaction. Our three speakers will present before the Q&A session. However, during their talks, feel free to pose questions and indicate to whom your question is directed to using the Q&A feature at the bottom of the Zoom window. And everyone can upvote the question posted there. Please reserve the chat function for technical issues related to the webinar and use the Q&A for questions to the presenters. We will then get to this question in a discussion session following the presentations. We also have a number of experts in the audience, so we want to encourage a lot of interaction. For the presenters, we will give you a warning when 5 minutes are left and when 1 minute is left for you to wrap up. Now, it is my pleasure to introduce our first speaker, Dr. Aiwo Dai. Aiwo obtained his PhD in atmospheric science from Columbia University in 1996. From 1997 to 2012, he worked at NCAR, first as a postdoc and then as a scientist. In 2012, he joined the faculty of the University at Albany, State University of New York, where he's currently a distinguished professor of atmospheric science. Aiwo has published in many areas, including global and regional climate change, Arctic climate change, hydroclimate, climate data analysis, Asian monsoons, diurnal variability, and atmospheric tides. He's a leading expert on precipitation variability and hydroclimate change, with an impressive large number of publications under his name. He's a fellow of the American Meteorological Society, and he served as the editor of the Journal of Climate for 7 years, and chaired the AMS Committee on Climate Variability and Change for 3 years. Thank you, Ewo, for being here, and the floor is yours.
Thank you for the introduction. So I'm going to share my screen. Okay, I hope you can see my screen, right? Put in. All right. Great. Thank you very much for the invitation to join this webinar and make a presentation. So today I'm going to discuss drought and the changing global climate. So I want to acknowledge my longtime collaborator, Dr. Temple Zhou at Chinese Academy of Science. So here listed several recent papers from which I will use many of the figures from those papers. So first I'm going to very briefly introduce the drought and how we measure it, and then discuss how aridity or drought may respond to global warming based on model projections, and then discuss a little bit on how the historic changes compare with the model projections in terms of spatial patterns. And finally, if time permits, I may address the several issues that have been discussed in the literature about the drought changes. So what is drought? Well, drought is often refers to the recurring climate events that harvest over land that resulting from below normal precipitation, and also associated with high temperatures over periods of months to years, number of years. It often causes lots of damages, and it's actually among the most damaging natural disaster. And in terms of formation mechanisms, drought often occurs under high pressure systems, persistent systems in the atmosphere, and the local feedbacks typically enhance drying under such meteorological conditions. And it has been shown that sea surface temperatures in the Pacific and the Atlantic basin can often lead to drier conditions or more chance for drought in the US and in many other regions. We care about drought because there has been a very observed phenomena in recent years, in particular in Western US. The last few decades has been more drought than used to be. How do we measure or quantify drought? Well, typically we use drought indices to monitor and quantify drought extent and severity. And many drought indices, such as standardized precipitation index, use precipitation only, and others based on precipitation and the potential evaporation differences. In my opinion, to assess the impact of global warming, we need an index such as Farmer Drought Severity Index, which consider the near surface water balance and derive and consider not only the input precipitation, but also the demand for moisture. And in such index, the changing temperature impact on evaporation can be assessed. If we use an index just used based on precipitation, then the drying effect from higher temperatures will not be able to assess it. Another point I want to mention for analyzing drought is that it refers to the drought refers to the left tail of the distribution of an index, and the distribution can have a mean shift that's often lead to a change in the aridity or the mean condition. That's not exactly the same as the drought. All right, and drought frequency can increase without a shift in the mean, just by changing the flattening the distribution and can increase the probability on the tail, right? So we need to distinguish drying or aridity change, which refers to the mean change in a drought index, or the drought change refers to the increased number of the least extreme events located represented by the often the left tail of index. So first, I'm going to briefly review the hydroclimate mean change. Again, this is a change in the mean, not the drought frequency, all right? But this is related to the drought change. So we have the precipitation change map on CME5 models, and evaporation follows very closely with precipitation change. So I want to point out that many subtropical land areas, you see a decrease in precipitation. That's often will lead to drier soils in the topsoil. And you see those areas, you see a large decrease in soil moisture, and even lead to a decrease in total runoff over those regions, right? Similarly, in the latest CME6 models, the precipitation change patterns, in particular dry in the subtropical land areas, still exist. Also, certain regions do see some regional difference with the CME5 model result. Again, the dry in topsoil is widespread, in particular in the Americas, and this is obviously not very good news for drought. Now, so here I'm comparing the CME5 model projected change in soil moisture with the CME6 models. You see this is in different unit, but still scale. Still, you see the larger scale patterns, they're quite comparable in terms of dry in Southern Africa, Australia, most of Europe, and most of Americas, in particular in the CME6 models, quite extensive, except a few locations. All right, so those are the mean changes. You could say drying in the mean condition. We need to look at the extreme events. That's on the left tail of the distribution, which refers drought events. So here I define drought as the events on with the index below the 20th percentile of the current climate. So this is a fixed threshold, all right? Future drought also using this threshold, and based on the Palmer drought index, you see this drying on the moderate and high emission scenarios over increased frequency, and so this is like over 100% increase in the drought frequency by the later 21st century. If we use other indices, soil moisture, total runoff, the soil moisture index gives you similar, even maybe bigger increase in drought frequency, but the runoff gives less widespread increase in drought frequency. Still, we see increased hydrological drought over most of the Amazon regions. Globally, you can integrate the drought areas on the 20 percentile, and by definition, current drought areas is on 20% of global areas, but that number can almost double under the high emissions, more than double on the high emission scenarios, in particular in the warm season. The warm season increases much faster than the other seasons. All right, that's another feature. So one question people often ask is that even though we do not see changes like in the total mean runoff of most areas, decrease only in the subtropic, but the model similar to drought frequency actually increases over much wider areas. The reason is that there's a change in the distribution of the indices. This is normalized runoff. So the future PDF becoming flatter with lower peak. So wider standard deviation over these different locations, besides the slight mean shift, and that increased standard deviation is widespread, not just over these locations, and that's lead to the increased frequency in hydrological drought as well. The change in the drought frequency can be attributed, in this case, using Palmer drought severity index. You can specify individual changes and look at the indices changes. And the conclusion is that most of the drying or drought increase is due to this temperature and the specific humidity change that's related to the increased water and vapor deficit in the near the surface and the rising temperature over most land areas. But in the subtropical regions, the decreased precipitation is a major factor for increased drought frequency. A third factor is the increased dry days or reduced raining days in model projections. This diagram just shows you that how the changing temperature and humidity can affect evapotranspiration and leading to drying and increased drought over land. All right, so I don't know how much time doing here. Okay, so next I'm going to briefly show you what the historical changes compare with the model projections of future climate. So when we look at the historic data, then we only have one sample, one realization, right? So in this case, I'm showing you the smooth precipitation average over southwest US. So and then compare with this in the decadal Pacific oscillation. So basically, this is the SST anomalies in the tropical eastern central Pacific. So if you happen to be just look at the last 40 years, you might see there's a downward trend. But if you happen to look at the earlier decades, you might see an upward trend. But in fact, if you extend to the whole data record, you would see this multi-decade oscillation, nothing to do with any long-term trend. So it is a challenge when you have only one sample, one realization to figure out what is the internally generated oscillations, what is the long-term change due to external forces. So that's a challenge we often need to consider. So on this map, I'm showing you three linear trend map for this period from 1950 to 2018 for name gauge based precipitation. This stream flow inferred surface runoff change. So these are two independent measurements, but variables are physically related. And bottom panel shows you the calculated Palmer drought index. So the point is that many of the regions, like of most of Africa, Southern Europe, Eastern Australia, you see a drying in all these independent, or these two independent index. This is kind of using the precipitation as well. But anyway, so all these three metrics indicating many areas have been see drying, but some regions like Central US, you see a wetting trend during the last 60 years also. And so, but this include both the forced and the internal variability. So when you compare to the model, multi-model mean, which represent many externally forced changes, you do see some areas like southern Mediterranean region, this drying appears to be Martinis and the southern Africa also appears to be consistent with the model projected drying. Other regions over here, also western, southwest, and northwestern Australia, actually see in the model as well. All right, so let's indicate some of the historic changes might already coming from the external forced changes. But if you look at the future change patterns, you see some substantial changes. For example, over Southeast Asia, the historic drying trend is absent in the future. It's likely due to like historical errors and other forces that not exist in future. And also this northwest Australia wetting trend is not existing.
Sorry,
yes.
You have 5 minutes left.
Okay, I'm going to quickly wrap up. So one more point I want to mention that the historical temperature warming trend have actually enhanced the drying in recent years, and that's mainly through the warming patterns, the lows and high latitudes. All right, and the final few minutes, I'm going to mention a few points despite the issues in drought research. The first point is that some papers suggest that the physiological response by plants on the higher CO2 will mitigate some of the changes. So we analyzed model simulations with only physiological effect. So the CO2 in the atmosphere is fixed. Only the plant see CO2 rise. And then another simulation is that the CO2 in the atmosphere affected radiation, but not seen by plants. So you can see the combined effect, the total effect mainly come from the radiative effect. The physiological effect by plants due to closure of stomata only have a minor wetting effect over most land areas. All right, so that's one conclusion. Another debated point is that some papers suggest that the dusty air in the glacier, in the cold glacier areas in the past might suggest a drier land surface. But in fact, there are a number of factors can lead to a dusty air in the glacier period. And the decreased soil moisture and the increased aridity actually is not suggested by model simulations. In this study by Jack Sheff, he actually showed to the last glacial maxima, most land areas should get wetter, not drier. All right, so to summarize, I showed you that the models suggest drier topsoils as the climate warms due to three factors. First, it's decreased precipitation in subtropics and the increased potential evapotranspiration due to increased water vapor deficit under rising temperatures over essentially all land areas. And finally, due to more dry days, reduced landing days. Second, an increase in drought frequency enhanced by a flattening of the distribution of soil moisture in the runoff. And thus, the mean change is not a perfect representation of the drought change. Hydroclimate change since the 1950s are still dominated by natural variations, in particular like ENSO, IPO, and MO. Also, the drying over certain regions such as Southern Europe, Southern Africa, Southeast Asia, and wetting over Northwest Australia may be partly forced because they are consistent with the model project forced signal. Plants' physiological response to elevated CO2 likely induce only a small wetting trend over land. The drying effect from rising CO2 from CO2's radiative or warming effect will dominate. The increased dust in glacial periods may not imply a drier land surface. Instead, dust may increase the dust load during those periods mainly results from reduced vegetation cover and the increased surface wind speed as well. All right, that's all I have. Thank you very much.
Thank you, Augusto, for keeping for your talk and for keeping perfectly the timing. Just a reminder that if anyone has questions, please use the Q&A box. So then after all the three presentations, we will read aloud the questions. So now it's my pleasure to introduce our second speaker today, Dr. Alessandra Giannini. Alessandra is a full professor in the Laboratoire de Météorologie Dynamique, the Department of Geoscience of the École Normale Supérieure in Paris, where she moved recently at the end of 2018. She maintains an affiliation as adjunct senior research scientist at the International Research Institute for Climate and Society of the Columbia University, where she worked for almost over than 15 years. Since her postdoc at the National Center for Atmospheric Research in the early 2000s, her research has focused on the climate of the Sahel, the cause of historical drought, predictability, and seasonal to interannual prediction, and more recently, attribution of past climate change. And this is most of the talk she will give us today. And one more thing, Alessandra is connecting with us from Dakar, where her presentation is also part of a local seminar at the Université Cheikh Anta Diop. So hello also to those joining from Dakar, and thanks to all you, and thanks Alessandra, and the floor is yours.
Thank you, Annalisa. Okay, let me see if I can, where is the presentation? Share my screen. Can you see the screen?
Yes.
Okay, great. Thank you. Well, let me start by thanking you, Annalisa, and for the invitation, and also thank my colleagues here who have been, as it works, the video here works that if I speak, it's looking at me, and if somebody else speaks there, it will look at them. So you're seeing me now, but there's a room with people following this from the university in Dakar. So well, thanks again. It's really good also. I think I've already noted some points of discussion with Aigo, maybe we can go into later, but let me then talk more specifically about 20th century droughts and recovery in the Sahel, and what we can say about the role of internal variability and externally forced change. Oops. Okay. Did the slide share?
Yes.
Happened in between these two figures that I'm showing you. And so this is roughly 20 years of research into understanding the cause of droughts in the Sahel in the 70s and 80s. And so it starts with attributing to the oceans. So attributing 20th century evolution of Sahelian rainfall to the influence of the oceans globally. And that's the plot at the top, where you see many of you, I'm sure, are familiar with these time series on Sahelian rainfall. In the figure on the top, the red is observations, and it's an average of stations across the region. And the blue is an ensemble average of with just one model. And the model is atmospheric model, and all it knows about the real world is the observed sea surface temperatures globally. So an atmospheric model responds to observed sea surface temperatures by reproducing the evolution use coupled ocean atmosphere models, and we use lots of them in what's called CMIP, the coupled model intercomparison project. And so this is the CMIP 5 generation. And in the bottom panel, the red line is still the observations. The yellow line is the multi-model mean of 29 models, if I remember right. And the green lines are the separate models. And so what I want to highlight here is the fact that this multi-model mean actually reproduces a decline in Sahelian rainfall. starting around 1950. So it's not exactly what was observed, but it's a decline in precipitation that begs the question then if, in the context of the CMIP simulations, where the external forcing and the connection to the real world comes from emissions, what anthropogenic emissions have done, but also natural, very natural changes in the external forcing, so in the energy that comes into the system. It's a different context, and so it begs the question of attribution. So what of these external forcings can explain this change in Sahel precipitation? So that's the beginning and the end. And then what I want to do is I want to fill in also with some physical mechanisms about how we can explain this evolution of Sahelian rainfall. Okay, and so my lens has been in these 20 years, it has been to work through understanding what the influence of the oceans is, because it started in 2003, and the initial result was it's the oceans that cause droughts. And so how do the oceans influence Sahel rainfall? And so then the connection to understanding change, ideally it's consistent. And so it has to be worked through what is the influence of these external forcings on sea surface temperatures, so that you get Sahelian drought, again, simulated by a different type of simulations and models. And so the idea is really to try and explain what the oceans can explain about this evolution. And then if that is not enough, then what are the missing pieces? Okay, and so this is just, I'm just giving references for reference, but I'll go through these 4 steps, and this is how my understanding of this topic has evolved. There's a lot more work, obviously, and so the stepping stones are, well, first, in the first paper, what really was highlighted was the role of Indian Ocean warming, and more generally tropical ocean warming. The second piece was a contribution from aerosols cooling the North Atlantic. The third was putting these 2 pieces together, and so coming up with a simple sea surface temperature index that actually takes into account both variations in global tropical warming and North Atlantic sea surface temperature variation. And then comes the piece about how external forcing, especially anthropogenic, influences the oceans and Sahel rainfall. As I said, there's a lot more work, especially on aerosols, the role of aerosols in cooling the North Atlantic since the 1950s. And so I just put some references here. And so it actually starts from just before my 2003 study that said it was sea surface temperatures, with this work of Rothstein and Lohmann. And then it continues with, so the focus here is mostly North Atlantic and sulfate aerosols, but it's also, what's also interesting is that actually it's consistent when you look at how volcanoes affect sea surface temperatures and rainfall. And then there's a little bit, not as much, and maybe here I'm missing, yeah, I'm sure there's more than this, but especially when we know in CMIP context, where you can also look at simulations that only have aerosols or only have greenhouse gases, you can try to separate these 2 influences. Then you can also ask the question of what is the role of greenhouse gases, especially when you look into the future. And so one important paper is this one by Dong and Sutton that says the recovery. It may be oversimplifying things, but it says, at least it poses the question, is the recovery of the rains after the droughts of the 70s and 80s due to warming and greenhouse gases? And in fact, we can come back and have a discussion at the end, but this is the big question mark, is actually the many different ways in which greenhouse gases can affect processes, and sometimes those are competing, and so it's complex. Okay, so in terms of the oceans influencing Sahel rainfall, so this is a plot from the first paper, and here in blue are negative anomalies that go with above average precipitation. So in fact, what happened in this model and in the real world was that if you imagine that it was, the blue is actually red, wherever you see color here, these are regions that explain droughts in the Sahel, so the historical drought. And so you see that specifically when you look at the long-term scale, the multi-decadal scale, it's really the Indian Ocean. But then also, as you probably know, El Nino also usually results in drying on the Sahel on a year-to-year time scale. So there's that element of warming of the Indian Ocean or warming of the tropical oceans, potentially drying the Sahel. And so that was the initial model, just a single model. And then if you look at the CMIP3 models and start looking at multi-model ensembles of simulations, then you see a similar response. You see the surface temperature at the bottom actually having a similar pattern of warming of the global tropical oceans and the Indian Ocean, but lack of warming in the North Atlantic. And this, and then you see the decline in precipitation all across the Atlantic ITCZ, Intertropical Convergence Zone. So this is when you compare 20th century simulations, and so you look at the end of the 20th century in these CMIP simulations compared to pre-industrial. Okay, the CMIP simulations here again are simulations that have all the external forcings varying, anthropogenic and natural. So you cannot really attribute separately, but it's an indication. This is an indication that there may be something that's externally forced that is producing these changes in sea surface temperatures and precipitation. So coming then to try and give an explanation, what I want to propose to you is first of all, this is how Sahel rainfall has been understood for a while. It's this idea that the interhemispheric gradient in sea surface temperature in the Atlantic controls the meridional location of the intertropical convergence zone. And then by continuity, this is extrapolated to land. And so the idea behind this fact that the northern hemisphere is cooler than the southern hemisphere is that the ITCZ tracks south, and so with it does Sahel rainfall. So you get a decrease in rain. What I want to propose to you is a somewhat different interpretation of the same picture that is composed of two pieces. The first piece is definitely the cooling of the North Atlantic. What is the contribution to the monsoon? It's that if you cool, you get cooler sea surface temperatures, you get less evaporation, and so you have less moisture in the monsoon, and so possibly less precipitation. So that's the North Atlantic side. The global tropical side is that the global tropics, and this is in analogy to work by Neeling and others, Neeling, Held and others, sometimes it's called the up ante, I guess. But in any case, it's an analogy to El Nino. When you warm the oceans, if you warm the oceans, you strengthen convection where it's warmest. But where convection happens actually has a global effect. And so it's the global vertical stability that is controlled by the warmest places where convection takes place over the oceans. And so if you warm and you strengthen convection, you also end up warming the upper troposphere in the tropics, and so increase stability. And so if you put these two things together, and then you're matching the moisture supply from the Atlantic to the threshold for convection everywhere else in the tropics, then it's actually quite remarkable that if you just look at the difference between these two temperatures, North Atlantic and global tropics, you can explain so much of Sahel rainfall variations in observations. And so this is simply just a scatter plot of this difference that we then, at some point, we baptized NARI, the North Atlantic Relative Index. And so this difference between North Atlantic and global tropical sea surface temperatures, and then an index of Sahel rainfall. Okay, so looking at this same NARI and explaining in time the evolution of Sahel rainfall, this is from data that's collected by AgriMet in Niamey, so it's a regional database. So you can clearly see over the 20th century the phases of Sahel rainfall, the very wet period in the 50s and 60s, the dry period in the 70s and 80s, and now what looks more like a variable period. So how do we explain this in terms of these sea surface temperatures? So the wet periods happened because the North Atlantic was warmer than the global tropics, persistently and consistently in the 50s and 60s. Then came the droughts, and that was because at the same time you had some cooling of the North Atlantic and then global tropical warming emerging. And now I think you see where I'm going. Now everything is warming, and so the system is kind of being pulled apart, and there's a lot of variation just because one year the North Atlantic can be warmer, and the next year can be an El Nino event. And so well, in any case, that's the interpretation. And how am I doing with time? I'm asking myself, but yeah. So then how this works also then when we look at seasonal predictions, and I apologize, this is a horrible figure, but just to show that, in fact, in a somewhat different context, but still using multi-model ensembles, those that are used to make seasonal predictions in the North American MME, there's a good predictive skill, even a few months in advance, if what you're trying to predict is the regional Sahelian rainfall, so just a number. And this skill, if you look at how models evolve sea surface temperatures consistently in a coupled ocean atmosphere system, then there's elements of, for example, this, I highlighted two models, one that predicts ENSO with skill, even in January, so trying to predict July to September rainfall, and another one that produces, predicts North Atlantic temperature as well. So it's really textbook of how multi-model ensembles should behave, that you put these models together and you get a good prediction system. And then the same, so the same fingerprint of this NARI is also in the CMIP simulations, in the sense that you can see here also, if I try to count, well, these are correlations of Sahel precipitation, so an index with global sea surface temperatures. And then if I count the models that correlate significantly at each grid point, what I'm showing you is that whatever you do, you kind of get the same picture.
Alessandra, sorry, you have 5 minutes left.
Yeah, okay. Thank you, Annalisa. So it's the same picture that we started with here on the right that you can also get with CMIP 5 models. So this is it's still always 20th century. Okay, and so actually this last bit is where we try to go a bit further, but with this is what also raises a lot of questions. And so with Alexei Kaplan, who is more of a mathematician, we actually we did this very simple, in a way, principal component analysis, where our elements that went into the analysis were the North Atlantic and the global tropics. And so playing with it mathematically, if you do EOFs on these two time series, you get one time series that looks like their sum and one that looks like their difference. And so mathematically, there's something that's justified. Well, I don't know. So one piece, the difference is the NARI that I discussed already. And the sum is more like a warming time series. And so this is how these two surface temperature components explain 20th century evolution of Sahel rainfall. And so it's through these regressions. So PC2 is like NARI. So it's the difference of North Atlantic and global tropics, and it dominates, especially in observations. And then the question mark that's left is PC1. What is the role of the warming? And so in 20th century, warming actually accentuates the drying. You could think of it that way. But this is not at all, I'm not showing you here, it's not at all consistent with 21st century, where in fact, you get warming and wetting of the Sahel in CMIP simulations. And so, yeah, I've not really talked, well, I don't know, I guess implicitly I talked about the role of aerosols and greenhouse gases, in that sulfate aerosols are implicated in the cooling of the North Atlantic that was observed post World War II, and greenhouse gases contribute to the warming of the global tropics. Yeah, so this is then to sum things up, it's exactly kind of what I said. I think there's a definite, my perspective is that there's a definite footprint fingerprint of aerosols and greenhouse gases in the Sahelian drought of the 70s and 80s. But that's really, this was a unique setting because of, specifically because of the aerosols around the North Atlantic that were there after World War II and have now pretty much disappeared. So the aerosols that were produced by the combustion of fossil fuels, especially coal in power plants, can explain the cooling of the North Atlantic from the 50s to the 80s. But now that, as you know, legislation has greatly reduced and abated these emissions of aerosols. It's the same aerosols and pollution that produce acid rains. So in both US, North America, and Europe, these emissions were really totally flattened out. I mean, if you look at time series from the what is it called, the European Environment Agency, you can really see that pollution going away. And so that explains also in part why the Atlantic is warming now. And so, but the point here is that so this was a very specific configuration to the 20th century, the fact that you had this interplay of aerosols and greenhouse gases. And so the drought of the 20th century is really not a prologue to how precipitation may change in the future.
1 minute, Alessandra.
Yeah, and then this leaves the questions that I highlighted in red there. Then what's the role of greenhouse gases and the warming that comes with greenhouse gases? Thank you.
Thank you, Alessandra. Thank you very much. As before, if anyone has questions for Alessandra, please post them in the Q&A box, and we will address them during the discussion session following the next speaker. And it's now my pleasure to introduce Dr. Juan Rivera, who is a researcher from the National Scientific and Technical Research Council of Argentina, named CONICET, working at the Argentine Institute for Snow Research, Glaciology and Environmental Sciences, IANIGLA, in Mendoza. He has a PhD from the University of Buenos Aires in the field of atmospheric and oceanic sciences. In his PhD research, he characterized the occurrences of meteorological drought in South and South America, analyzing the main spatial-temporal features of these events and their atmospheric and oceanic drivers. During his postdoctoral and ongoing research, he focused on the central Andes of Argentina, analyzing the propagation from snow deficit to the development of hydrological drought. He served as a lead author of the Working Group 1 and the 6th assessment report of the IPCC. Juan, the floor is yours.
Thank you, Matilde. Thank you, all the organizers, for the invitation. I hope my screen looks well. I will talk about some of the mechanisms behind the recent unprecedented drying trend in the central Andes of Argentina. Here you can see a nice picture of the environment we are going to talk about. So in order to place you, we are located I work in Mendoza, in a province located in Western Argentina, near the border with Chile. And most of the water used here for the development of most of the activities in Central Western Argentina, I need to point out that this is an extremely arid to semi-arid region with precipitation ranging from 150 to 600 millimeters per year. And it's home of most of the wine production in Argentina. So if you probably go to a supermarket and pick up a bottle of wine from Argentina using the calibrated language of the IPCC, it's extremely likely that you will find wine from this region. And all these activities are possible due to the rivers that are used for the irrigation. what we call agricultural oases that you can see in dark green in the map in the left. So there you will have all the wineries, most prestigious wineries in Argentina. Unfortunately, during the last 12 years, and still ongoing, there was an observed reduction in snow accumulation over the higher elevation of the Andes Mountains that triggered hydrological drought conditions over the region, affecting, of course, winter tourism. There was limited snowfall for the functioning of winter tourism. Also, water for irrigation and the development of agricultural activities, and also for domestic use. Moreover, some of these basins are transboundary basins, so that led also to conflict between several provinces in terms of water use and water availability. In the bottom right, you can see some pictures that are really recent about, this is the major dam that provides water for 1.5 million inhabitants here in Mendoza City. And you can see that it's less than 50% from the total capacity. So it's an extremely period that was persistent over the last 12 years. So first, what I want to do is to characterize this drought event based on several indicators, and then I will show you or try to identify which are the major mechanisms behind this drying trend. And some of these results have been published recently with some other colleagues from Argentina and other parts of the world. So I will be happy to provide this presentation so you can have all the information available in these recent publications. We use some hydrological drought indices to characterize the hydrological drought conditions. Some of the most commonly used indices, the daily varying threshold level method, using the streamflow equally or exceeded the 70%, 80%, and 90% of the time as indicators of moderate, severe, and extreme hydrological droughts, respectively. You can see in the right a time series of observed streamflow in blue and the threshold level in red, and you can see that when the observed streamflow is below the threshold level, you can define the start and the end of a drought period, and you can calculate also the volume that is missing in that river in order to calculate the severity of the drought. So you can identify the frequency, the severity, and the duration of this kind of events using daily streamflow records of the region. In the map, you can see a lot of points, orange points. That's where the streamflow stations are located. So we have a decent network for monitoring streamflow of the region. And also, if you see the stars, you will get snow accumulation data. And then we use the most famous standardized streamflow index that is based on the standardized precipitation index, which is for a time scale of 3 months, which characterize the streamflow deficit in terms of the standard deviation relative to the long-term mean at a given location. And in the right, you can see a graph where we can define the hydrological drought conditions, where you can identify different events with a determined duration and severity. So using those indicators, I will show some results based on these recent dry conditions. We have 15 rivers monitored by the water agencies in central western Argentina. So an homogeneous period of over 50 years can be used to monitor hydrological drought conditions. So all the time series will start in 1971 and continue till near present. And you will be able to see, we calculated for the upper panel the annual number of dry days, which are the days where the stream flows were below the selected threshold levels. And you can see 3 colors indicating 3 severity levels for this drought period. And what is and this is a regional average for the result from all the events. You can see the last 10 to 12 years, an unprecedented duration in terms of dry periods or low stream flows. And if you see the standardized stream flow index for all the 15 rivers, you can see that an homogeneous behavior, because all the rivers are fed by snow, by snow melt. So you can see that these drought periods are consistent in time for all the basins. When we see the volume, we see mostly the same as in the graph that showed the duration. I mean, the last 12 years, you see bars with larger volumes in these 5 selected basins. And when we standardize that volume with the capacity of all the dams available in the region, you can see, for example, that in the case of Potrerillos Dam, which is the dam that provides water for most of the population in the region, until half of 2020, the drought accounted for almost 11 times the capacity of this dam. So it was really significant, the amount of water that was missing due to this snow drought period. Now, I will try to link now what we are observing in terms of surface water availability and what happened in terms of snowfall. So the graph in the upper part shows the snow water equivalent anomalies, and you can see this period of 10 to 12 years of consistent negative anomalies of snow accumulator that triggered these hydrological drought conditions. You can see in the graph below the percentage of basins with hydrological drought conditions, and you can see from 2019 onwards an increase in drought severity, with most of the basins experiencing extreme drought events. And you can see a picture also from one of the dams in central Mendoza, and a snow pillow in August 2017 that is the middle of winter, and you can see barely no snow at all. So that's the kind of picture that you get if you go to every single winter in the last 10 to 12 years in the region. So it's pretty dramatic in terms of the availability of water for all these socioeconomic activities in the region. Then we can link the lack of snow to the health of glaciers, which are also a relevant source of water for the region. And we have an observatory of snow cover for Argentina and Chile, which is showing also this prolonged period of below normal snow cover over the region, and thus also affected the mass balance of the main glaciers of the region. If we see an example from Ferry and co-authors from a glacier in headwaters of one of the major rivers in the region, the Atuel River, which is showing a negative mass balance between 2000 and 2018 that is mostly due to the lack of snowfall in the last decade, from 2009 onwards. So you can see that the mass balance in the first decade of the century was positive or neutral, but the last decade was particularly harmful for the health of these of these ice bodies. And also you can take into account the temperature that was also increasing over time. And this is also a mass balance study covering much of the glaciers in southern South America, where you can see also in the last decade, all red colors indicating that glaciers were losing mass. So in summary, I like this figure because the water reserves for the region, we are losing these water reserves due to the drought, the ongoing droughts over the region. So finally, I want to summarize some of the mechanisms that we were analyzing in the last years. I want to show this picture in the left, where the main features of the atmospheric circulation over South America are included, and you can see the position of a semi-permanent anticyclone in the South Pacific that tends to move north during the winter and leave space for these mid-latitude storm tracks to move north and to let snow accumulation during winter, particularly over much of the Andes in Argentina and Chile. So that's the main source of snow for the region during winter. These storm tracks interacting with the moist or the humidity from the Pacific Ocean and creating snowfalls over the region. So one of the mechanisms that was precluding this to happen in the last 10 to 12 years was the position of the anticyclone that was moving towards the south. And that was linked to the Hadley cell expansion due to increasing greenhouse gases. This expansion was studied in a previous research project that I had been lucky to participate, which called TEAMS, where we analyzed how this anticyclone moved south, and that created drought conditions over much of central Argentina and Chile. This is also evident if we analyze the composite of the anomalies of hypothermal height at 500 hectopascals in mid-troposphere. So you can see this increase in pressure over much of mid-latitudes in near southern South America, and also an intensification of this low pressure area over near the Antarctica that also increase or intensifies the westerlies, and that also provides a mechanism that precludes these mid-latitude storm tracks to move north and to generate precipitation over the SADE area. And this is linked also to a positive trend that was observed in the southern annular mouth, in particular since the 1960s, and also this trend in the position of the southern hemisphere Hadley circulation edge in the southern Pacific. So those mechanisms are creating that the mid-latitude storm tracks that can't progress north and provide snowfall over the region. And one of the last mechanisms, yes.
5 minutes left.
Perfect. One of the last mechanisms that we were digging into, I forgot to mention, but those are anomalies during the last 10 years, approximately. So they are capturing, in particular, what happened within this drought period. And if we see the sea surface temperature anomalies, you can see also a pattern where there was a positive anomaly near 30 to 40 degrees south, in particular near the position of New Zealand. And you can see that this is an emergent trend, for instance, in the last 30 to 40 years. So some colleagues from Chile provided some explanation for this kind of mechanism, where this enhanced warming in this particular area affected also the storm tracks, created or contributed to these observed trends in atmospheric pressure, and also provided a drying mechanism for the study area. But I don't want to forget about the effect of La Niña, which seems to be not really there if you see the SST anomalies over the last 10 years, but we did a previous study that calculated the sea surface temperature anomalies for the first 5 years of this drought period, and you can see a La Niña pattern over the SST sea surface temperature. Then came one of the biggest El Niño events in the last century that obviously masked this or obscured this kind of negative sea surface temperature anomalies. But we have to keep in mind that from the interannual perspective, La Niña events tend to generate also a mechanism that precludes these mid-latitude storm tracks to progress towards the north and to provide snowfall over the region. If we see some of the climate projections for the rest of the century, in particular considering 2 degrees or 4 degrees global warming levels, you can see that the drying trend will continue in the future, in particular over much of central Argentina and Chile. And this is also linked with a projected trend in sea level pressure over much of the southwestern Pacific. And this was also projected to, if we consider some of the metrics that can characterize the age of the Hadley circulation, in particular what Julian Villamayor and co-authors investigated for winter precipitation in green, and the edge of the Hadley circulation in red. You can see a coherence between these two mechanisms, and that which is also evident in the other graph in the right.
1 minute. Extra.
Yes, just to summarize, we characterize this hydrological drought event not only considering stream flow, but also considering snow accumulation and also some of the available glaciers evolution. This drought was mainly triggered by a strengthening of the semi-permanent anticyclone of the South Pacific Ocean, and a southward displacement and a deepening of the low pressure band in the vicinity of the Amundsen-Bellinghausen Sea near the Antarctica, and also warming surface waters in mid-latitudes of the Pacific in what was called the Southern Blob. And also we identify some that La Niña conditions can play a role at interannual time scales. And future projection shows a continuity of this drying trend, so a higher probability of facing more hydrological drought periods in the future is there. So with this, I want to thank you for your attention. I'm happy to answer any questions.
Thank you, Juan, for your talk and for this overview over this region of South America. Okay, I see that there are questions already in the Q&A. Aiguo already answered to some of them, but there are, for example, a few unanswered. So I think we can start for a round of question 1 for each, and then see if there is some question for all of you. So Aiguo, I will ask you, following this question from Agathe So, thank you for your interesting presentation. I noticed that in the figure of CME6 model projected drought frequency, the 2 drought indices show opposite patterns between the West and the Sahel, some kind of dipole. How could you explain this West-East contrast over the region?
Yeah, great question. When I just went to look at the precipitation change map, so the center on the eastern side of the Sahel, the CME6 models project increased precipitation, but near the west coast areas, the models project decreasing precipitation. So that's, I think, a major factor for those contrasting changes in drought frequency. So precipitation pattern, different changes over those western and the central eastern part of the Sahel region appears to be quite different in the future projections, and that's a major driving factor. Temperature, I don't think temperature changes may be similar. So I think it's mainly due to different precipitation projections.
Can I add something to that? Can you hear? Oh. No?
Sure.
Yeah, I mean, with respect to what I was discussing, that the 21st century is very, very different in projections of Sahel rainfall. There's quite a bit of work that tries to understand how to go from 20th to 21st. But one idea I'll just throw in there, because I think more needs to be done, is that the monsoon strengthening also means this heat low strengthens. And so while it brings more moisture into the center and east of the Sahel, it may actually be advecting relatively colder or less humid air from the northwest into the very westernmost portion. So it's the dynamics of a stronger monsoon that actually may explain why this dipole east to west, but it's something that definitely needs more attention.
Yeah, I as Sandra discussed in the historic period, the SST change patterns in the Atlantic is very critical for that Sahel region. So in the future, in future scenarios, the aerosol forcing are different from historic forcing. And the Atlantic SST response to future forcing will be critical for Sahel rainfall change patterns. So, but I think the models still have quite large uncertainty in terms of regional precipitation change around the Sahel region and Central, even like Eastern Africa as well. So there are some uncertainties over there as well.
There is a question to Alessandra too, related to the role of both anthropogenic SST warming and natural multi-decadal SST variability in modulating the interannual SST teleconnection with Sahelian rainfall. We found, Roberto Suarez says, that the Mediterranean impact on the Sahel seems to prevail over ENSO and tropical Atlantic impact. What's your opinion about this?
Thank you, Matilde. I'm completely at odds with this idea that the Mediterranean and its moisture may have any much of a role with the Sahel, and but I'm very open to discussing this. But what I see, because I see in climatological terms, you know, that also goes back to some work by Neeling and Cho on the what limits the poleward extent of monsoons. One limit is this dry air advection from the north, and so when you're considering that you're converging onto a warm and wet region, which is where it rains, the advection has to be drying. I don't understand how you can get moisture advected into this region from the even if it's from the Mediterranean, because the moisture gradient, I just cannot understand anything else besides this fact that the moisture gradient goes against this idea that you can import any relevant moisture that contributes to precipitation. Yeah, I don't know, but I agree it's an open question because yeah, statistically. So maybe I would throw back: is it really something? Is it really something specific to the Mediterranean that's not included in some kind of North Atlantic signature?
Okay, thank you. There is a question also in the chat for Juan. Thank you for your presentation. I appreciate the illustrations that you used. Ingrid is asking, what other approaches apart from a physical mechanism do you think would be useful to explain droughts?
I think people is really concerned about also the impact of water management in water availability, not only what is happening in the higher elevations of the Andes, but also what is reaching to the irrigated areas. So those kind of processes, for instance, the infiltration and the aquifers recharge, we are not looking at, and I think they are relevant. Snow sublimation is really relevant because we are in a dry environment, and most of the snowfall that doesn't end in the river stream flow. Much goes to the atmosphere again. So we are losing some of the water source that we are not accounting for, and we need to include also not only in situ measurements, but also satellite information and more detailed model outputs for the characterization of these kind of processes in the region. And also, I think water management is a relevant aspect that can help society to understand if drought is just natural or anthropogenically driven by climate change, or is also exacerbated by a misuse or a mismanagement of water.
Thank you. And as we mentioned at the beginning, as Alessandra is doing her presentation from Dakar, and there are people there, so I don't know if there are questions from the audience there, we can also consider a couple of them. Do you know, Alessandra, if there are questions on your...
Questions? Would you like to pose a question? No, Ania?
No.
Yes, yeah, I think so.
Okay.
Good. Maybe you need to speak up, Nolaini, so the video can...
Okay, I have no question for our host, but I have a question for Dr. Dai about the using of farmer outness. I don't know what is the motivation of that, because there are other parameters that use the water balance. I don't understand that.
Maybe Alessandra, can you repeat aloud, because it was not much, because if you can repeat.
Okay, the question is to Aigo, why use the Palmer Drought Severity Index and not other measures like water balance, you said, Nolaini? Yeah.
Good question. In fact, in our papers and also on my slides, we used, besides Palmer Drought Index, we used the soil moisture and runoff loads normalized to a standard unit, deviation unit. So we used 3 different drought indices based on soil moisture, based on total runoff, based on Palmer Drought Index. The Palmer Drought Index and the soil moisture from the CMIP models, they all already consider the effect of changing temperature, changing wind speed, changing radiation, changing humidity. So they are consider effect not only from changing precipitation, but also effects through potential evapotranspiration through those surface meteorological changes. So and I showed you the soil moisture and the Palmer Drought Index. They are essentially indicate similar drought frequency changes in terms of spatial pattern and magnitude. So let's give us some confidence. The soil moisture data directly come from the CMIP models. So we just analyzed the model output using normalized into unit of standard deviation. So the Palmer Drought Index, I think it's useful, but it can be combined with other indices as well.
There is another question to Juan. There are two questions. One of them is related to Pascua glaciers. Can you tap for Pascua glaciers for irrigation? I don't think so.
I'm not sure where are Pascua glaciers located. I'm not aware
Okay.
of it.
And the other question is, could you comment something about at which extent could CMIP models reproduce correctly climate trends and variability in the region? Do you consider really reliably their future projections, CMIP models and the region?
I think, yes, I think that the trend is well captured. I don't think the internal variability is adequate yet in CMIP models, but I think some of the regional aspects of this decline trend in precipitation are well captured, and the mechanism within the CMIP model outputs are coherent with this. So I hope CMIP 7 will make it better in terms of other kind of information that we can take into account for the future and for also this near present characterization. But I think it's something that we need to point out, that models are doing well, at least from a regional perspective.
Thanks.
Thank you. And there is another question for Alessandra from Rowan Sutton. What is your view on the relative role of internal variability, including AMOC, and force changes for explaining changes in the Atlantic SST relevant to Sahel rainfall? How might this differ between the past and future?
Well, thank you for the question. I mean, definitely, it seems that there's something besides external forcing in the very wet period in the Sahel in the 50s and 60s. And so, but yeah, if that is Atlantic multi-decadal variability, I mean, I'm open to hear what you think about it. Yeah. The other components, I mean, some it's clear that there's some element of external forcing in Atlantic, but in Atlantic multi-decadal variability in this aerosol influence. But how do we go about separating things? I really have no good thoughts around that for the time being. I don't know if, yeah. Yeah, so it seems to me there's definitely room for, yes. I'm not doing it. No.
And so
Yeah.
one,
Yeah.
okay, thank you. One other question to the three of you. And so considering your different prospects and expertise, if you can give priorities, what do you think are the aspects that are most important now to consider if we want to improve our understanding on droughts and possibly be helpful in terms of information that you can provide to the society? So it can be data, missing data, modeling processes, theoretic understanding, whatever, from your perspective. So you can answer one by one, starting from Aigu or Alessandra and Juan.
I'm sorry, I did not quite get the question. Is it for both me and Alexandra?
Yes, for the three of you, different perspective you may have.
Well, I actually want to comment at the last question about the AMOC's influence or AMO's influence on Sahara rainfall. I think as Alexandra already pointed out, that many papers already have tried to attribute historic aerosol and other anthropogenic forcing on driving the AMO variability during the last 100 years also. And we know that Sahara rainfall is closely correlated with the AMO SSV index, but that the historical SSV index are partially driven by aerosol and other decadal forcing during the last 100 years, in particular last 60 years. So there's a significant contribution from those external forcing to the recent Sahara landfall changes. But exactly what percentage of the observed landfall change, like the drought in the 80s, 60s, 70s, is due to the aerosol forcing, and how much is due to the internal generated AMV or AMO oscillations, I think that's still not quite clear. But I think the literature suggests substantial contributions from both external forcing and the internal variability, and they happen to be in phase during the last 60 years also in the Atlantic SST. So that's something I want to add to.
Okay, thank you. So we are going toward the end, I'm sorry. We have to wrap up and close because it's almost time between 5:30. And so again, thank you to all the speakers that participated and give their talks, Aigu, Alessandra, and Juan. And again, thanks for your excellent presentation and for answering all the questions. Many thanks also to all person online and for the attention and the participation today in the chat and for the questions posed. This is, as again, I remind that this is a series of webinars, so that occurs about every 2 months. So there will be something else planned for around April. So watch the space for the announcement soon. So again, thank you to all. Again, thank you, Matilde, for helping moderating. Thanks, Nico, for organizing, and all the WCRP groups that contributed to this work. And bye, everyone, and enjoy